Okay, we're live, it looks like. So we're going to be streaming directly to YouTube today. I think I seem to have a greater audience on YouTube, so I feel like they would appreciate YouTube live videos that may pop in their feed and they can interact with rather than Twitch. Maybe in the future I'll dual stream to Twitch and YouTube. At the moment, it's going to be YouTube. So yeah, today we're going to be going part 4 of our PCI Python driver. And this is going to focus on using debugging the Microblaze on each of these devices over PCIe with kind of like this Python API. So, first news, we're going to go here. So, if you look in the description of the video or the live stream, um, right here, we have a repository for what I've been doing this project. It has the hardware, it has the software running on the RISC-V processors on the Microblaze, it has software running on the host system, and I hopefully will be updating on this. It just has some simple Tickle and Python scripts to generate all the files. But that is the moment. There's not really a big description. The description will probably be later. I do like how there's like this really nice balance of HDL files, Tickle, Python, C, and System Verilog. I kind of like that balance. Nothing really wins. But yeah, so we'll be going through, I'll be using this repository kind of to go through the code so far, and then we can look at on the server of how the debug works. So going back here, we're going to do a quick review. We have our PCIe system. Let us make this full screen. Pop it out and make it full screen. Will that work any better? So we have our PCIe mass connection here through AXI Lite, and it is connected to this AXI switch, and that has GPIO that we use for resets and DDR paging, the debug bridge, which we'll go over today, a hardware ICAP, which we use for warm boots and fault injection and partial reconfiguration, XADC, which we use for temperature. We also have that hooked up to the DDR controller because apparently if you have the XADC and DDR at the same time, you have to have a temperature to them. Other than that, and then it's the Quad SPI. Then we have our main Microblaze. It's kind of running my application code, and it's connected to the DDR along with our 3 designs under test. And these are either like a Microblaze design under test or a RISC-V design under test. And the you go to here, you go to the DUTs, the design under test. We have the Kronos, the Pico RV32, Tiger processor, and the Vex RISC-V processor, as well as the Microblaze. So we have 5 processors that we're doing these tests on. We may look at talking about that test later, but here I'm trying to talk about the PCI Python development and not so much what the application code is about. So, quick overview. We've gone over ICAP. We've gone over XADC, the QSPI. We need to update the QSPI. Might update that later today. But we'll see what happens. We've done the DDR paging. So today we're going to talk about the transceiver and loading software into the Microblaze. So, to begin, let's follow the code. So we're going to go into the host software, and we're going to begin with the PCIe device. So there's a few things in the PCIe device we want to talk about. So first we're going to talk about the Tickle client here with the XSDB Tickle Server. Then we're going to talk about the XVC, which is a Xilinx virtual cable. Then we're going to talk about the Microblaze object. So there is one shared Tickle client among all my PCIe devices, but each one has its own Xilinx virtual cable and its own Microblaze object. So I'm not sure if anyone's familiar with XSDB, so we can pull up XSDB. Where would be the best place to pull it up? Do I have it? Give me a second, I gotta plug something in, and then we can look at XSDB on my computer. Okay, we're back. So, we want to look at XSDB on our computer, so let's pull up the Vivado Tickle shell. So we have Vivado. We're going to start XSDB up. We're going to connect to a local thing, a local hardware server. So this is a local hardware server. And then we do targets. And I have a BCU 1525 or a DCU 1525, which is Vertex UltraScale 9 Plus. It currently has a Microblaze running on it. Cool. But we also do JTAG targets. We see that it is using the Xilinx. This is an FTDIO device. We have the UltraScale Plus with the ID code. An IR length of 18. I didn't realize that had such a big IR length. Wow, that's really big. Then we have a B-scan switch and other things, which is interesting to look at. So, and this we can do like FPGA-F. We can do a lot of commands here. We can program the FPGA. Where is it? We can do breakpoints. We can look at memory. So if I do like help memory, we can read and write memory, modify, do all these different things through here. We can also help registers. We can read and write registers. Not very useful. Help thing, but so we can do several commands through the Xilinx. Was it the Xilinx XSDB? I'm not sure the S is right in the beginning. XSDB, the Xilinx system debugger. Okay, but it's a Xilinx system debugger. Very useful. I use it all the time. It's very similar to XSCT. XSCT is a Xilinx software command line tool. Very similar functions. You can type connect in here. It's like, okay, XSCT is a superset, so there's like additional, like, I haven't really seen what the additional things are, but I usually use XSDB because it's usually sufficient for my needs. I haven't seen anything special by XSCT, or yeah, XSCT. So we don't need to, that's basically all we have to worry about. So XSDB is something we pull up, but XSDB is hard to interact. There's not really like a good API. And what I've seen with OpenOCD and other things, you can set up a telnet client with it. So what we do is, so XSDB runs Tickle. And so here's our XSDB Tickle Server Python code. And it defines that we're going to use the local host, we're going to use the port, and then we're going to do some multi-processing with Python, and we're going to run the process XSDB start. What XSDB start does is it's going to run the XSDB with the specific Tickle file, and we can go into how that Tickle file works. So this starts up the Tickle file, and then otherwise, this function can open a connection to the Tickle server, the telnet Tickle server, and we can send commands and receive the outputs of it. Close the server, and I use this to check if we do like a Control-C that it'll like do a nice close down and not an ugly close down. Let me see if I can show that real quick. So like right here we have a keyboard interrupt. If there's going to be a keyboard interrupt, we will kill all the virtual cables and we kill the Tickle client properly. So let's go look at the server.tickle. So the server.tickle doesn't do much. It sources a package index tickle, which references this Tickle server, which we'll look at. That's the next file over. We run the Tickle server, and we configure source line view 0. This prevents additional output, or I can't remember what this does. Let's go look at what this does. I do not remember. What does... Oh, okay, yeah. So this is a symbol error, and I just wanted to get rid of it. So it doesn't look for symbols anymore. So it just looks for, I guess this is a very simple source line view. Okay, so nothing too exciting. It's just operating this, and this is a very simple code. Basically, we start a server, we connect it to a specific port, and we take, and this is kind of like a hook on any incoming messages. And basically, all we do is we're going to execute that message, and then return that result. And I put an end there, so if there's a multi-line code, it like makes a whole list, and you can actually do multi-line return values. And that's basically how we're operating here. So we turn on XSDB. We make it so we can access it through a kind of this Tickle Server connection. So, okay, now this is our object that's shared among all the objects. So this is a class object that's shared among all the instances of the object. And then we create the Xilinx virtual cable. So the Xilinx virtual cable is the code that takes the raw JTAG commands and sends it over to PCIe. So see, we're going to look at the Xilinx virtual cable. Here's our registers. We have a register for length, TMS, TDI, TDO, and a control register, which is basically, I can't really remember what the control register does at the moment. There's a start. Oh, we got bits for it right here. Yeah, so there's just a start. It's supposed to be mask, not mash. Okay, that's cool. So XSDB, we're going to start a server, and starting the server, we're doing another threading of Python, so these servers can run separately in the background, constantly going and sending and receiving messages. And this one, we basically have a port, and I don't think I wrote that, but that works okay. So we have the IP and the port. And the port I have defined as default as 4000, but if we look over here, it's going to be, the port is 4000 plus ID, and ID is just incrementing the devices on the thing. So this server basically creates a Xilinx virtual cable. And the Xilinx virtual cable is just this kind of raw JTAG messages that they send back and forth. And this is the get information. This is like, I believe, the set clock rate, and this is send a command. And these indexes are magic numbers. It's just me kind of playing around with the different bit indexing. I'm pretty sure we could do a cleaner method for it that doesn't require so much calculations. This isn't very optimized. It's just trying to work through it. But I would like to do a cleaner method. I also want to look at doing a method where so this is communicating with this debug bridge. And this debug bridge sends these like JTAG messages across to this DMDM. But I'm wondering if we do our own external vscan. I guess the vscan's more complicated than the average JTAG. I was just wondering if we could do like our own. But yeah, things to look at. Because the debug bridge here has many options, from AXI to bscan, from AXI to JTAG, JTAG to bscan. Maybe we could do JTAG to bscan and send it raw JTAG commands, and maybe that would be faster. But I don't know. This is all going to different options, so it could be a little bit messy. But basically, what this code does is the PCIe writes the JTAG values here. So if we click documentation, the product guide, if my product guide pumps up here. Okay, here. So here's our register space that we had earlier. So here we have register length, TMS, TDI, TDO control, and this is all we're really doing. Yeah, we're just passing in the length of the bits to shift, the TMS, TDI, TDO, which is an output vector. I'm not sure why you would ever write to it, but you only really read to it. And we are basically and so we're just enabling the shift operation. We're never doing a loopback. That's another bit, but we're just enabling the shift operation. So this is how we sending the raw JTAG messages over PCIe. This is how we can communicate with the processor. So we now have a Xilinx virtual cable for each PCIe device. Now we still haven't got how we can communicate with the Microblaze. So that's kind of next. So once we get the Xilinx virtual cable up and running, after we get all the other stuff, we want to do a Microblaze find target. So in the Microblaze, we're going to, when we create it, we're going to connect XVC. Where do we create the Microblaze? That's a good. Oh, here's where we're creating the Microblaze, and we pick the client, IP, and the port. So when we connect to it, we send this command right here, and this says I want this. We send this to the Tickle client, the XSDB Tickle client, and we say I want you to connect to the Xilinx virtual cable at this port or at this address in this port. We send it to the command, and next we want to find the target. So that's the command we're running here. So I have 23 different Microblaze targets on, so we have to find out which target I want to look at. And how we do that is we're going to filter. We want to look at a Microblaze. We want the JTAG cable serial, which is going to essentially be the port value. And I'll show this in a second. We can look at the JTAG values. If I can remember how to print them out. It's like properties or something like that. But that'll be but we can try to look at that in a second. And then we try to find a command. If we can't find the command, we try to resend it, trying to see how we're doing. So our next commands is that we have a Microblaze read, and this is basically allowing us to read any amount of data. So we pick the target, and maybe we can show you these commands by hand. I'll show you these commands by hand real quick, and then maybe we can use an API to look at it. And then we tell it to memory read. We give it the address. We give it how much we want to read, and then it parses it out and returns the array. We can send a reset command. We can get the state of the processor, and we can also download an ELF. And this basically is just picking a file that's local to our Python program, and we can download that ELF file. Let's see what's the best way to do this. So we're going to open up my server, and I'm going to kill the current test. Okay. So log files. So we're going to look at main. Well, we're going to look at main. And we're going to look at PCIe device. So we can get this up and going. So first, in PCIe device, I don't want to download this, because this will start doing fault injection. I don't want to do fault injection, but we can do everything else. Everything else is pretty benign. And then then we're going to take out the PD log, do this, and we'll just print every 60 seconds as it waits for exit. That should be good. So this is going to take a while, but this will be fun to watch. So let's close. Did it automatically save? automatically saved. Find out the fun way. So we're going to go back to that directory. We'll zoom in nice and big. So this is going to take a while, but kind of cool. So we'll get everyone to watch. And we're going to do it in a screen because it works well there. So we're in a screen, so we can detach it and look at it later. So what we're going to do is sudo python.main. Okay. Ask for the password because we need the password for all what we do. So we load it. We launch the XDB with the Tickle Server, and now what we're doing is we are setting up each device. And each device setup has a rescan. We load some stuff over DDR, and we're not downloading any Microblaze code. But that's kind of where we're sitting at the moment. But we're not logging anything, which is okay. Yeah. So why this goes? Let's look at what we have on. So we're going to do Control A D to detach it, and then we're going to do our own XSDB hardware server bin. Cool. So to do connect here, right? So connect will automatically connect to the same hardware server, so we have all our JTAG targets, and we're slowly adding more targets to it. JTAG targets, and there's a way to print the properties. I think we can do help JTAG. So help JTAG device properties, right? So we can just do JTAG device properties. We'll do 0. I think we want target properties actually. Help target. Oh, right there, target property. So we do targets, target property. Get all the properties. So I know this is kind of hard to look at with the screen zoomed in, but here is our first Microblaze device, and we're looking at we're looking for JTAG serial. Right here, JTAG cable serial is the IP plus the port. So that's cable 1, or cable 0, cable 1, cable 2, cable 3. Okay, cool. And now we have loaded this up, we now have all these targets. So the commands we're looking for, so if we do targets 3, right, that's a Microblaze. State, it's running, yay. We can do a memory read, 1, 2, 3, 4 of that address. We can do a memory read 5. And we can read additional addresses. We can read 9, which is where the TUT is outloading the values I expect when the TUT is properly working. They're all the same. But yeah, we can read those values. And then we can download a file. So we would just do we just help DAO, right? So help DAO, it's just DAO and then the ELF file you want, and there's different options. Nothing really interesting here, but you can do data if you just want to download a binary value at a specific address. So we have the ability to look at this, but as I said, I have 23 Microblazes, and this is just going to continue to grow. Let's see where we are in screen. So we're going to exit this, go back to screen, retach. So apparently I can't scroll up. Go up here. No, it's just screen. So what device are we currently on? Reading zeros across everything. So we did device 1F. So let me show you where 1F is in the tree. The PCIe-T, LSPCIe, LSPCIe-T. So we are currently at 1F. 1F is right here. So we've done these two, we've done these three, these three, these three. So we're probably starting on the 12th device right now. And we still go all the way to 34. Yeah, I think that's the 1F we're talking about there. Unless there's a different. That was these values it's referenced. I guess it's that 0, 8. What we were immediately removed. So we do screen dash R. So this is 2 0. Oh, it's doing fault injection on it. No! Okay, so here's it's doing the fault injection because I forgot that it logs the files. So we're gonna go ahead and kill that. Yay. Where was that? That is not something we. I don't want you doing fault injection on my system. Oh, I know where it is. We have this log right here, so let's grab that real quick. No, no, no doing additional fault injection. So let us look at this. So we're gonna just probably do a different range of devices. Remember how to do this well. I want to just do what? Do 3 devices. Oh, well, we'll need all the. Yeah, well, this works. So we're going to kill this screen, and now we're here. So we're going to do sudo python to try to have an interactive terminal where we show how we can do this. And if we can paste, yeah, paste that. Oh, the XSDB doesn't work very well in the interactive terminal. It gets in the way. Try to start a device. I remember that from last time. I'm not sure there's a good way to then be interactive with the device. That's a good question. How are we doing on the video? 30. But yeah, I think that's. Can we get into it real quick? I think so. XSDB is taking. It's going one or the other. So we basically wait here. And what was the last command? I want to do. Like switching between them. It's garbage. It's absolute garbage. Oh, okay. Exit. So we exit here and then back in. I guess if we don't have an interactive mode, or if we do it in a server that's separate. Yeah, I'm not sure a good way for Python to have an interactive mode, to have that run, but not let it be take over standard IO or standard. I guess the idea is that we maybe want to try to run it separately. We could try to run it separately. So what we do is we go here, right? Wait, how does it reference it? Good question. How does it need this interaction? Yeah, I guess it's something that's not really usable in interactive Python. Message share. No. I guess we just pass in the whole log. No, but we don't have access to the object. Unless there's a way to get that object. A different thing. But the Python interactions are probably separate. Yeah, that's a fun little puzzle. My current solution, we can't do that. So, get this back and rolling. But that's the easy way, and what we would do to increase the functionality of our little debug processor is we would just add more commands here, and we could support the ARM as well. There's not really a PCIe ARM device though, but we could support JTAG interfaces. But Microblaze is usually the main one. I do not have support for the ILA, the internal logic analyzer. That one, Xilinx doesn't really have documentation for, but I guess you could connect to it as long as you have access to it. But yeah, that seems more complicated. Worth. Okay, well there you go. We kind of demonstrated the code for the Microblaze. And feel free to look at this code, the comment code, to make a request. This is kind of just an application to get stuff up and running. And we're using, as a reminder, I guess we're using the Squirrel Acorn 215 Plus because it's the best speed grade. We're using this device. This is also similar to the Night Fury or the Night Fury Light Fury public repository. So very similar to exact same schematic, looks like that. They have a 100T L2 on this and a 200T L3. So pretty much matches the Night Fury. Like I have more DDR than Night Fury of 1 gig. So, but if you want to get this product, just I don't know, hit up eBay. Let's see. We have to open it up. I don't. So you guys see what my stuff is. Squirrel Acorn 215 Plus. Yeah, we got some working ones. Fuji Nest 148, not bad price. That's not a plus. It needs to be a plus for me to be happy. That's a plus though. This is a plus. So it's a usable one. But yeah, so we'll be posting more. I think tomorrow, if I have time, I need to figure out a good stream schedule. They may be sporadic at the moment, but I need to get the QSpy reliable in programming. So that may be something we look at tomorrow, maybe later today. I might do some preliminary stuff today to try to get it to read and write reliably. Okay.